Record on this computer and we'll get started. All right. So today, like we were talking about beforehand, we're going to have a workshop on social network visualization. Also, my computer is now running very slowly, I think, because of the PowerPoint and R and Zoom all at the same time. So if you cannot understand or hear me, let me know, and I will figure out some way to make it better. But so we're going to go over some basic ways to visualize social networks. Here's this fancy title slide that has no real relation to the topic, but I just thought it was cool. And also apologies to people here who were already in the networks class last spring. We're going to be going over a lot of the same stuff, but I hope that it's a useful refresher for you all. So just first, what is a social network? Many or probably all social phenomena involve relationships between things. People, businesses, governments, NGOs, social actors broadly interact with one another. That's why they're social. And these interactions are often of huge theoretical importance in social science. And we can model this activity as a network of actors and their relationships. And we have a theoretical reason for thinking that our data is relational, is reflecting interactions, and the outcomes of interest in our data are dependent on the actions and outcomes of other actors, or the larger network structures we are connected to, the embeddedness aspect here. You probably should model your data as a social network, or at least that's what social network scholars say. So just some key terms that we're going to go over real quick. So node is /actor/vertex is the little dot in the actual networks. It doesn't have to be a dot, it can be a square, it can be whatever shape you can put on there. Edges, ties, links are the lines that connect the dots. Those represent the relationships of interest in the network. And then the graph or the network is the whole collection of nodes and edges. And then just also real quick, we have degree centrality, which is a network statistic for a node that is just the number of edges it has. So for instance, Doug over here, he has 5 edges, so he has a degree centrality of 5. And as you can see, degree centrality can be directed. So in this one, or it can represent directed or relationship. So for this one, I hope it's not a friendship network, because that would be sad for everyone in here, because it's all unidirectional relationships. But Doug has the most in degree centrality. The lines are going toward him, right? Versus away from him, out degree centrality. So network visualization, why is it important? We want our network visualization to be able to tell a story. Who is in the network? How are they relating to one another? And what relevant traits seem to be structuring the network? Is there any community formation occurring, for instance? And obviously you need to do actual network analyses to test many of these things, but visualization should provide a useful basis for readers of your research who want to understand your more complex analyses. And also remember, unlike my first slide of this presentation, you should foremost want the network visualization to effectively communicate to your audiences. Do not make something overly fancy just to impress the reviewers, though that does sometimes work, unfortunately. All right, and here are some ways to visualize networks, because it's not just the stereotypical network maps that we saw, but we have just basic statistical charts. Not shown here, but is related are there are summary tables of network statistics that are increasingly becoming popular among network scholars, because when you deal with really complex networks, it's pretty hard to visualize them in a way that actually communicates useful information. And so increasingly we're going back to boring old just tables. But we also have here heat maps of matrices and arc diagrams, which I have not used. And we can also do hive plots and biofabric graphs. I have no idea what these are. Honestly, they're too fancy for me, but they are different ways of visualizing networks. But today we're going to focus on the classic network map, which is generally what people think of when they think of a social network. It has the nodes, it has the edges. They're all connected in some sort of very fancy looking formation structure. So here are some general tools and guidelines for network visualization. So these four important aspects of network visualization here or tools are color, position, size, and shape. These can both be edge and node or node attributes. So for instance, you can color your nodes, you can color your edges to represent edge. Which maybe something is someone is friends with somebody versus like a romantic relationship. You might color those edges differently. You might color the nodes differently if somebody is older than somebody else. Network position matters a lot because you don't want to fool people into thinking that there is, if you don't have any sort of significance to network position, you don't want to fool people into thinking that there is. That's sort of something that is an inherent assumption among a lot of people, is that if there's a node that's floating all the way out here on the edge of the graph, it must mean something that it's so far away, but it does not necessarily. And then so just general good tips for layout aesthetics. You want to minimize edge crossings. It's very neat. You want uniform edge lengths, again, for similar thing, for the reason I just talked about with the position. You don't want to trick people into thinking that the distance between nodes matters unless it actually does. You want to prevent overlap of nodes just because it's very clean, and you want symmetry because people like symmetry. So this is an example of a network visualization. It's a Jackson Pollock-esque painting or painting-esque image of a network of music artists created by actually the inventor of the main network package we're going to use today, iGraph. Ties here represent strong similarities in musical style. I don't know how that was measured. And the nodes are the music artists, with the colors being the genre, size of the nodes being the popularity of the artist. And then the edge attributes are the colors represent betweenness centrality, which is a network attribute or network statistic. Transparency is the importance of the edges between the actors. I don't actually know what importance here means. And the graph here is actually force directed, which is a technique for network visualization, which uses an algorithm to make network visualizations aesthetically pleasing. So it minimizes edge overlap and attempts to equalize edge length as much as it can. So as you can see, creating network visualizations for large, complex networks is quite difficult, even for the experts. With complex networks, simple statistical tables are often the best form of visualization, even if they are not the most impressive. Or else you end up with something like this, where looks very, very impressive, but also I have no idea what is going on. And then here's an alternative network visualization that the creator offered to try and clear up some of the, communicate some of his desired points better. But we're not going to be getting this fancy today. Also, here is a great clean visualization of a bipartite network of Mafia members and summits they've attended. I chose this totally at random from the internet and definitely did not use it as an attempt to ingratiate myself to any specific professors. But as you can see, the shape and colors and sizes of the nodes are, are communicating things here about the Mafia members and the summits that they attended. So for today's example, we're going to make a network of sociology graduate students here at UNC Chapel Hill. Apologies to the non-sociology people in the audience. You will not be in the data, but everyone else here will be. And we are going to do it based on shared research interests between sociology graduate students. So the nodes are going to be the graduate students, and the edges are going to be sharing at least one research interest. I got the data from the UNC Sociology grad student website. The research interests, I only took 3 per graduate student, the first 3 that were listed. I also combined a few of them to just create more general categories, because some people have very specific things that are part of broader, like, you know, health or immigration. And I also gathered data on cohort year and year of undergraduate graduation to see if there are any interesting patterns that we can see when we visualize this in the network. So share, switch over to R. All right, so this is our This is an R Markdown file. If you're not familiar with R Markdown, so for instance, if you are a first year in our department, you will get very familiar with R Markdown next semester in TED Stats class, where you will grow to both love and hate it. Love it because it is a really great and neat way of organizing R code. Hate it when you've spent 2 hours because the document will not knit correctly. And then eventually you just give up and email TED and say, TED, I'm sorry, I don't know what's wrong with this. Please tell me how I can get this to knit in the future because the code runs fine until I try and knit it. And that happened to me probably every single homework assignment in that class. But so for today, the network visualization stuff. This first chunk here, so this our chunks are just the coding chunks here in between these little apostrophes. This first one is about the knitting function. Like I mentioned, knitting is just taking the, is what happens when you, after you're done with the document, R Markdown can upload it into your code and your output into a sort of neater, more like you can even make it into a presentation, like neater, presentable document. In this case, the output is set to be HTML, but usually you want it to be like PDF or Word or something. And we don't actually have to worry about this, but I'll run it anyway. And so this is an R code chunk. The nice thing about R Markdown is that it only runs things in between the R code chunks themselves. For instance, so whatever is written in here can't even be run. It is just a, you can leave notes for yourself. You can write things like Santa Claus is not real. And it will not run, and R will not learn that Santa Claus is not real until next year when it notices that many of its presents under the tree are, say, made in China on the back by the barcode. But also here are some useful packages that we're using today. iGraph and readr. Really, iGraph is the only one that's about network visualization. readr is just for uploading the data from CSV files. All right, and we're going to download the data from GitHub. So, oh, there's download progress. Installing the packages. We're going to download data from the GitHub page that I set up. So, library first, readr, run select lines. Oh, wait, I see that there's stuff in the chat too real. And then we're going to upload first an edge list of relationships in the data, and then node attributes. So the edge list here, which we can see with the heading, is a list of every single tie in the network. So I think that there's over 1,000 ties in this network, even though there's only 60 something grad students. So even with sort of a small amount of actors in the grand scheme of network analysis, this can get very big very quickly and very complicated. And so this head command just returns the first 6 rows of this. And also we can see here some of the node attributes if I run this part. So here's a list of the graduate students. Are any of us on this first? Jenna, there you are. You're here. Has your cohort and your undergraduate graduation year based on the information in the grad student website. Cohort information I might be slightly off on. For people I didn't know, I used the Wayback Machine and then went through the grad student website year by year and like tried to add people to make sure that I was getting the correct cohort dates because there were some issues with it. But all right, so now we can actually create network data with iGraph here. So just load iGraph. And we should check the class of our data sets because iGraph needs iGraph objects to run. Class of the edge list, the data frame. Class of the node attributes, also a data frame. But we can take the data frames and turn them. Well, I should also explain what an edge list is, by the way. An edge list is one way of constructing a, or of structuring network data. So like I said, it is every single tie in a network. Alternatively, you could use an adjacency matrix, which is like a row of every possible actor, a column of every possible actor, and then a 1 or a 0 representing whether or not there's a tie. there. Edge lists are generally more efficient, less computationally expensive, and easier on the researcher. But if you have isolates in your data, which means that there are actors or nodes where there are no ties, then edge lists aren't going to be able to capture them. But we don't have any isolates. And even if you do, actually, you can combine the edge list here, as you can see here on line 40, with a node attributes data that can then add in isolates to your general network data. But so yeah, this line 40 here combines the edge list with the node attributes to create an iGraph object. Should. Then we can check iGraph. Perfect. And so we can also view some important information about the iGraph object here. Just sort of a word dump, but basically it's the description here is listing node and edge attributes along with a little bit of the network ties that we saw earlier. So we have vertex attributes only here, or node attributes, with the VC meaning vertex character, vertex numeric, VN is vertex numeric, but you can have GC, graph level character attributes, or for instance, edge level numeric attributes from VN. And if you look at the top line of the description, UN dot dot or dash dash here is not Morse code. It indicates that it is an undirected graph with named nodes. So our nodes each have individual labels to them. The dash dash here means that the graph does not have weighted edges and is not a bipartite graph. So alternatively, a 4-letter code of D-WB would mean that our graph is directed, does not have named nodes, has weighted edges, and is a bipartite graph. Let's see. Oh yeah, and then the numbers here, 63 and then 1,109, represent the number of actors. So we have 63 graduate students and 1,109 number of edges, 1,109 relationships based on shared research interests. And then here we can look at some other useful information. So the edges of the object, again, this is giving us some of the ties. Not going to show us all of them because that would take up a lot of space. We can look at the vertices. Here is half of the grad students about. We can look at vertex attributes, cohort. So here's a list of all of the different cohorts, or each vertex's cohort here. And then we can also look at undergraduate graduation year. And we can even find particular nodes by their attributes. So for instance, if we go cohort 2020, here is my cohort. Here's Meg, me, Grace. I think that's everyone from our cohort that's in here. And then we can also look by undergraduate graduation year, which is also the year that I graduated. So you have Grace, me, Athena, and Meredith here from the our workshop today. And you can examine the network matrix directly. So this will show all of the ties in, I believe, row 1. Let's see. If it loads. Okay, so whether or not there's a tie with whoever is row 1. So whoever is row 1 does not have a tie with Yunlin, but does have a tie with Sarah, does not have a tie with Ken, but does have a tie with Inez, so on and so on. And then whoever is row 5, column 7, whoever those two individuals are, they have a tie together. So once the data is uploaded and properly formatted, it's actually pretty easy to make a simple network map in iGraph. But warning, it's not going to be very pretty. So yes, here is the network of all of us, our shared research interests. As you can tell, you cannot really read anything. Jenna, there you are at the top by yourself. You have a few ties, 1, 2, 3, 4, 5, 6. The issue with yours, Jenna, was that you had your third interest was organizations, which nobody else had listed in their first 3. So I only had 2 interests listed for you, so you had less ties. I'm sorry. But yeah, so like I said, it's not a great visualization. And also you can rerun it and you will see. it totally rearranges things. So Jenna still at the top, but now Michelle at the bottom over here. I think I'm right there in the middle somewhere. Very hard to tell. Jenna won. Yeah, she did. The network has determined it. But so one thing that we can do to try and make things a bit cleaner is remove the vertex labels. So here's the same graph without vertex labels. I don't know which one you are, Jenna. Sorry. Presumably still at the top somewhere. But now we don't know. So this is nicer to look at, but now we don't actually know who anyone is. And also all the node sizes, colors, shapes are the same. So it doesn't really tell us much about the underlying like processes going on in the data. Also, orange and gray is not a great color combination, in my opinion. So you can adjust the plotting parameters in iGraph. I'm actually not going to run this because it tends to make things weird on R when I run it the past few times. It slows everything down, but basically it opens up. Oh, actually, it's still open here in the corner over here in my bottom right help tab. It shows you all of the possible ways that you can adjust the parameters of an iGraph object using iGraph. So, and we can adjust these directly in the plot function itself. So let's double down on the orangeness of the plot to show why it's not a great color, and to label the nodes by, let's label the nodes by cohort instead of name. Error in lot, can't find function lot. Plot, oh, I didn't highlight the P, I see. There we go. There's no errors in this code, I swear. And then here you go. Very, very ugly. Again, all orange now, and no names, just cohorts. But you can see that you can very quickly adjust the parameters within the plot itself without it becoming permanent to the iGraph object. But if we want to make it so that we're having a consistent sort of layout, we can add attributes to the iGraph object itself. So let's do that. Let's set the edge color. So the tie color is going to be gray 80. I don't know why 80. I think maybe it's just a slightly more transparent gray. And then we're going to generate colors based on year of undergraduate graduation. I know there is an easier and more elegant way of doing this, but I really tried to do it that way and it did not work. So I defaulted to just manually assigning colors to every single graduation year, which we will do again right here. And we can see all of the colors that we have. And then we will plot them. So here is a gumball machine of the department. We have, as you can see, some interesting stuff going on here with trying to remember which cohort is which. I'm purple and at the bottom. Is that true?
I'm purple. I'm 2019.
Oh, you could be right in the middle, or you could be toward the top again. But we can clarify that in a little bit. But first, we're going to change the size also. So this computes degree centrality, so the number of ties per actor. We can use that to set the node size, which, as you can tell, it's really ugly because some people have way more connections than others. No offense to this tiny purple dot. I think that is you, Jenna, there at the bottom. But to make it a bit more legible, we could just divide the size by, or the degree centrality by 3. So this is better. There you are again, Jenna. Even tinier, but much more comparable to the rest of the nodes now. Interestingly, the black nodes here, which I think represent people who graduated in 2012, remember? Yes. Seem to be pretty big. So whoever is here in the department who graduated from 2012, they have research interests that are shared with a lot of people in the department. And now we can set the shape of the nodes to reflect attributes. So this here, I already ran it, is the names, potential names of shapes that we can have in the for the plot. I don't actually know what the difference between a C rectangle and a V rectangle and a rectangle is, or what a R or raster, R raster. I don't know what these are. I just know square, circle, rectangle, sphere, the basic ones. But again, here we can manually assign them based on cohort and run it. So let's do that. Also, I did selfishly make the default color and shape for both my cohort and my graduation year. So I am the red circle on here. And actually, I guess so are Grace and Johanna, who's not here, but they are also people who came directly out of undergrad in 2020. But here it is, divided by shape. This is very, very ugly. Apparently, they use this little network symbol as its own shape. I don't know if you all can see that. Really weird. I think the clock looking thing is supposed to be the pie chart. I don't know why they would do that, and this is just really not very useful. So we're going to make it just older cohorts versus new cohorts. I think we have I separated it by the 4 newest cohorts versus the 4 oldest cohorts in the data. And this is a little bit nicer. So new cohorts, circles, old cohorts, square. And yes, red circle, red circle. And then finally, real quick, just wanted to go over potential ways to do network layouts. So you can do the default algorithm layout is this one right here, layout underscore width underscore FR. I don't remember the actual name of the algorithm. I'm sure Scott does. And that's plot it. It's going to give us something very similar to the last one. It's trying to make things neater than they actually would be randomly, surprisingly, but it is still not super, super neat. We can also do some other fun layouts that will be illegible. So you can do layouts in a circle like this. And then we are all in this fun little serrated tire. But you cannot tell anything really about the edges because they all overlap terribly. We can also do layouts on a grid, which again, not really telling us anything, but a bit neater than the circle at the very least. Also, I don't know why, but it looks like the edges are breaking at the top there. That is not my fault. That is something with the function itself. We can do layouts randomly. So this is what it would look like if it's totally randomly. It's graphing outside the plotting margins. Thank you. Totally randomly, just random placement of everything. Layouts as trees. I know from looking at this data earlier that Yunlin is this pink square up here. For some reason, in a lot of possible format, she always ends up being like by herself. Like there's one I did earlier as a star, and she was the very center of the star, and then everyone else was around her. So I guess R finds her to be special. And then we have spherical layouts, which is just a somewhat messier circle. But really the best layout that we saw probably is just the base default algorithm here that we keep returning to. Cool. All right. So that was only like half an hour. But does anyone have any questions?
I have a question that's
Yes.
a little adjacent. I'm really curious, did you hand collect the data or did you collect it in a quicker, fancier way?
I hand collected it. It was really annoying. And I did some like shortcuts in R to like rearrange it more easily, but I did spend so much time on the UNC grad student website getting everything situated. Honestly, if I had the code for that here, we could have taken another hour going over it, all of the stuff I did trying to get things set up for the workshop. But once you have like the network data like structured correctly, like everything else runs pretty smoothly in my experience.
Could you talk a little bit about getting like the data structured? So like how would you even start to like build a data set that would do this?
Right. So you either need to, like I mentioned, or the two most common ways are create an edge list or an adjacency matrix. So what I did was I went on the website. I made this. Let me see actually if I still have the Excel sheets because then I can show you. Um, Share. Can you see the Excel sheet actually? No. Okay. So I made this Excel sheet, and here's how I grouped sort of the different research interests together. And then I went through, and I believe that I there's an easier way to do this. Scott is going to be mad at me for not doing it in the easier way, but I sorted this basically column by column, took everyone who was tied together, made them into a vector in R, and then I permuted all of the possible combinations of that vector to create all of the pairs. And then I did that for every single column. And then I printed that back out to Excel. And then I rearranged it in Excel so it made one just giant edge list. Instead, I can see Scott typing. And I then took that edge list and uploaded it into R. That is not a great way of doing it. Alternatively, what I was starting to do was set up a matrix of people, and then I was going to do ones and zeros manually, and then I was like, that will be terrible. I'm going to try and figure out a shorter way of doing it. But yes, Meg, you have a question?
So this isn't a question. This is like potentially an easier way to do this would be to treat this as an incidence matrix. And then Scott is nodding. Yes, I remembered this. This is like what I did for my paper for Scott's class. So like, because then you can just project it. If you've got people connected to research interests, you could then project from the bipartite network into a unipartite network. I suspect you can also with an incidence matrix potentially go directly to connections among people by the other variable, but the way I would think about this matrix would be as a bipartite people to research, and then projecting into people to people connected by a shared research interest. So that's another way to do it.
All right, that is, if we ever do this workshop again, I will be sure to modify to do it that way, because it was terrible doing it the way I did it. Yeah, I think for mine in Scott's class, I just did it manually, which also sucked, was bad, but I only had like.
As a projection, it's like 4 lines of code.
Really?
Yeah, it's super
4 lines?
super easy. I don't think it's even 4 lines. I think it's 2. Because you run the once you have the code for the graph, you run just like the code that creates the projection, and then you name like which level you want to be using. I can send that to you, Jacob, and it can go in whatever drive this sort of stuff belongs to.
Yes, please. No, do that, both for my master's and for and for this, so that I save time and don't pull my hair out going through Excel sheets and 4 hours trying to rearrange data. Oh, there's Meredith's cat. Yes, Jenna.
Yeah, this was an awesome presentation. Thanks so much for the explanation. I also just wanted to put out there, I spent several hours yesterday trying to figure out how to make a map and a network. So if anyone is interested in that, I have some code that figured it out.
Oh, like an actual map in terms of like location?
Yeah, so like I have my network on top of a map of Massachusetts. So that can use the like a map object from R and combine it with a network object, which was surprising it wasn't an iGraph object, but that's also an option.
Yeah, I was originally going to try and do something like that for this, but then I was like, that's going to take way too much time, and I'm already only getting to the layouts really. But I was going to do maybe this in a future workshop, like interactive, like network visualizations, do stuff with like changes in networks over time, and then yeah, mapping also, because I was originally going to do undergraduate or like college like location. And then I was like, that's going to be difficult. I'm going to change it to year because that's listed on the website already. Any other questions, comments, easier ways for me to have done this besides bipartite, unipartite network stuff?
I can jump in with a few more tidbits and tips if we're looking for network
Of course.
visualization stuff. So Jacob, I think you based a lot of the code from today on Olga Karatidou's network visualization guide, and she runs a lot of network visualization workshops at the major networks conferences. So if people want to take it to the next level and get some insight about ways to visualize dynamic networks, import external images and things like that, that's a great resource. I think one thing that's useful to think about as well is really when you're picking a network layout and a way to visualize it, thinking about what piece of information you're trying to convey. So the default algorithms or plotting algorithms that we often see in iGraph are like I think it's Fruchter-Reingold is what it's called. And it's just a default thing that's supposed to be kind of generally elegant. But what it does is as the network gets more and more interconnected or larger and larger, it starts to look more and more like a hairball. And so depending on what types of structural features we're trying to accentuate or amplify, we actually get different types of stories that are communicated through the data depending on how we visualize it. So an interesting thing about network data is there's actually an infinite number of ways you can arrange the same network on a grid space or outline it in a graph. And so we have a lot of flexibility in terms of what features of a network we're trying to draw attention to. And so different algorithms tell us slightly different types of things. For instance, a lattice type layout can tell us something about nearest neighbor selection and clustering patterns. We often get our eyes kind of drawn to who is connected to whom in this kind of ring shape. If we're using like a dendrogram or a tree hierarchy, then we're often implying some type of hierarchical structure or connectivity. The clustering gets less attention drawn to it, but the degree centrality and the ordering of vertices according to degree centrality actually start to get sorted for us. So depending on what type of hypothesis you're trying to draw attention to or what type of finding you're really trying to accentuate, you often want to pick a different type of layout algorithm to really communicate that information more clearly. And this is really critical, especially when you're doing a presentation where the visuals kind of demand more attention than they do in a type of paper. So I think often it's really, when you're thinking through how to lay out network data or visualize network data, not only thinking about what looks cleanest or prettiest, but what really communicates the information I'm trying to highlight, because we have a lot of flexibility here in how we want to draw attention to it. Another thing I'll say is that we can, one thing you can do, and this is very common when we're either comparing between networks or we are plotting the same network over time, is you can plot multiple network figures on the same grid space or the same plotting images. And you can manipulate this using generic R parameters for outlining figures in R plotting space. And one thing that's useful in this is you can actually store the layouts from a network and treat them as fixed positions. So you can plot different graphs over the exact same node layouts for a fixed network size. And that means if you want to highlight change between different types of networks over time, you can fix the node layout so that only the edges are changing and that shift in dynamic structure is really highlighted. So again, we have a lot of flexibility in how you choose to lay out network data and in terms of what information you're trying to draw attention to, depending on how you choose to plot. So I think the visualization step, and Jim Moody has written a lot about this, about how critical visualization can actually be in understanding what's going on with network data.
Great. Yeah, no, thanks for that, Scott. Yeah, I had written in my notes, stress that layout is about function, not aesthetics, but the way I said it made it sound like I was just choosing the prettiest one. But basically all the other layouts I tried out were for fun. There was no real, they did not provide any extra meaning or anything, but cool.
So I think this is actually, if you scroll through the graphs that you have, I think this point is kind of made kind of clear, right? So like
Mhm.
if you go up, what was the one where Yunlin was like on top?
Layout is tree.
Yeah. So if we look at that, we're kind of pushed towards thinking about the network as hierarchical, right? Because it's already sorted in this kind of vertical layout. We see one person on top that has a lot of spanning, and there's actually not a lot of clustering. And then beneath it, we have a ton of interconnectivity. So it's hard to look at this graph and not think about it in terms of outliers and hierarchy. But when we look at a different graph, we're kind of cued to think about it in terms of like the standard Fruchter, Lineman, or Reinhold, or whatever it is, layout. We're kind of cued to think about it more in terms of just dense interconnectivity rather than who is on the margins. And so again, kind of the story that emerges from the data is often really informed by the choices we make with visualization.
Anything else to add? Scott, if you want to keep talking for another 15 minutes, filling time. No worries.
We don't have to, but I mean, do people want me to talk about minimal graphs? Because I think, well, I'll just do a sidebar here, and then if anybody wants to see code, I can pull code up. But one thing that's often helpful with network data as well is we often communicate our theory with minimal graphs rather than actual data. And so if we have a theory about how a structure causes a tie to form, or the pressures of a structure for creating a relationship, one way to communicate this is often with just creating a minimal theoretical example, 3 nodes or something, and then show a triad forms. And so one thing we can do with visualizations is often kind of create these minimal graphs in a way that clarify what's often kind of an abstract network structure and show how this theoretical process works. So I'm just gonna like pull up a minimal graph on my computer. So this kind of thing, right? So what we can do is take something that's essentially abstract, create an arbitrary figure, and just isolate how a particular structure emerges or forms based on a network visualization. And these types of things are really trivial to create. I mean, it's entirely simulated data. And so all you're doing is creating a matrix that represents what you want it to represent, and then outlining how the process unfolds in a completely theoretical sense. And if you're pursuing something in the networks world that relies on a structural process, most people who aren't networks researchers, they have a hard time conceptualizing what it really means for a substructure to have an influence. But if you put like a minimal graph like this out there and stick the figure in their face, all of a sudden they can be like, oh yeah, it's a shape, I get it, okay, right? So it makes something that's abstract all of a sudden very, very tangible. And so this is another way we can kind of utilize network visualization to build a theoretical case. It doesn't only have to be kind of the empirical component, what does our data look like, but what is the argument we're trying to advance or the story we're trying to tell, and show how it unfolds in a very literal way. Do we have any final thoughts or questions before we wrap up today? Cool. Thanks everybody for joining us. Grace, what do we have next on the docket in 2 weeks?
I believe Chris Brem is coming in to share about some of his research on statistical sampling. I think it's in 2 weeks. Check